problems may be there. Otherwise, he will not do in that way. So we are waiting at least, I think, more than half an hour for Professor Kundu's talk. I'm extremely sorry to the participants. In fact, if Professor Jayakumar is ready, let us start his talk for the time being. And in the meantime, I shall contact Professor Kundu again. And if he is ready, there is no problem. We can shift his talk to the second session. What about Jayakumar? Hello?
Okay. Whether we may have to wait for some more time? Is it not?
So we are waiting for. Yeah. Now it is too late. Okay. It is about 10:38 time. Okay. So we have scheduled it at 10 a.m. and we, in fact, the join started from the 9:45 or 50 onwards. Everyone are waiting. Okay. About 70 in the meet are waiting, and some more are outside in the YouTube and the other streamline.
Okay, then we can start. Okay.
Yeah. Okay. With the permission of all the participants and my professors, Kalyanam sir, Professor Devas, I think Professor Kusubovsky is also with us, and other professors from various parts of the world probably may be there in the group, and my students and other other researchers from various parts of the country and in fact from the globe itself. With your permission, let us start the session. Second speaker, start the session with the second speaker, Professor Dr. Jayakumar. Is in fact we are very proud about him because he's also our alumni and he's heading the Department of Statistics, University of Calicut, and he has several. In fact, it is there are a lot of works he done in the area of distribution theory and related stochastic time series, stochastic plots, etc. related areas. As well as personally, he enjoying several positions also. With the bless of God, we have a great personality like him with us to handle this session. With the permission of our professors and our other delegates, I invite Dr. Jayakumar to please carry over this session, and thereafter, Professor, let us listen to Kundu. Professor Jayakumar, please.
Yeah. Thank you, Professor Sadish, my teacher, Kalyanam sir, and all the participants. First of all, I take this opportunity for thank the Department of Statistics, University of Kerala for having this workshop on distribution theory. And today's my talk is on, my lecture is mainly on applications of completely monotone functions, in distribution theory. So this is in fact a classroom type lecture, mainly focusing on the applications of completely monotone functions in deriving probability distributions, and how these completely monotone functions and Weinstein functions help us to study the various properties of distributions and related stochastic processes. I hope the screen is visible. Is it okay?
It's okay.
Oh,
It's okay.
okay.
Can yeah, you can. I think it is the largest full screen, isn't it? It's okay.
So,
It's okay.
uh,
Okay. Make it full screen.
Expanded.
Yeah, check whether it is full screen or not. I doubt.
yeah, now
Yeah, now it's fine. Now it's
now
fine.
it's fine. So I am talking on applications of completely monotone functions in distribution theory. So it mainly depends upon there are some functions where their derivatives have the property that their sign in fact changes alternatively. So before looking into that, first of all, I may take some examples, and that will tell us that it is essential for us to develop newer and newer families of distributions to describe the real phenomena in a more appropriate way. For that, let me analyze some certain data sets and to show and to see how their histogram behaves, and to check whether the conventional distributions will help us to model that data sets. So that is our first aim. For that, I may take some data sets that are available in the literature. That is, the first data set is the lifetime of 50 devices in weeks. And it is the lifetime of 50 devices in weeks are collected in an article by, which is presented in an article by RSET, which appeared in IEEE Transactions and Reliability. And if you want to model these lifetimes, you can see that the histogram corresponding to the data set that I have shown earlier behaves like this. And naturally, the question is that whether there is any, if you find the frequency curve corresponding to this histogram, and if you look at the available distributions that are available in the literature, we can see that most of the distributions, that is the exponential, gamma, Weibull, Pareto, etc., may not fit to this situation or may not be able to describe this data set appropriately. Right. So, or in other ways, you may be able to find some other distributions, or you may be able to find what is the mathematical function that is able to describe this phenomena or the phenomena of the lifetime of these devices appropriately. So that is the case of this data set. Let me look for another data set. So this is the breaking stress of carbon fibers in an experiment that is available in the literature, and it is appeared in the journal Quality and Reliability Engineering International. And in that paper, you have the breaking stress that is given in the data set. And if you find the histogram corresponding to the data set, it is like this. So the question is that which is the distribution that is appropriate for modeling data set? So it may be skewed, whether the normal is appropriate, whether skew normal is there, or skew Laplace is there, and so. And this is another data set, that is, this is the number of cycles to failure of 2500 centimeter specimens of yarn. That is again a data set that is available in the famous book of Laplace on lifetime data. And if you find the histogram corresponding to this data set, you can see that the histogram corresponding to that data behaves like this, which means that you have from the interval 0 to 100, you know the histogram, the bar length, you know, and from 100 to 200. 200 to 300, 300 to 400, and you can see that 400 to 600 there is no observation, and 600 to 700 there is a little number. So now the question is that whether which is the distribution that is appropriate for modeling. Is it exponentially there, or Weibull follows the Weibull distribution may be able to can be used to this model this data set, or the Pareto, or any of the or inverse Gaussian and so on. And you can see that the answer to this question is that the most of the distribution that you are familiar in the literature may not have the capability to describe this distributed data set appropriately. And this is another data set which appeared in communications in statistics, theorem methods in 2000, which described the survival times in 46 years of patients given chemotherapy treatment. And if you look for the survival times in years, that is the survival years of the patients, and if you want to model this data set, you can just look at this. The data set is like this. That is, you have 0 to 0.5, 0.5 to 1, you look at the bar, then 1 to 1.5, 1.5 to 2, 2 to 2.5, 2.5 to 3, 3 to 3.5, 3 to 3.5 to 4, 4 to 4. What does it mean? You can see that you may be able to see a decreasing pattern from 0 to 2, then there is slightly increasing, then decreasing, and there is no observation in the interval 3 to 4, and then there is an increasing one, then decreasing. So which is the distribution that you know in the literature are available, are useful, appropriate, more appropriate for modeling? So that is these types of things, when you as an experimenter or as a practitioner, when we look for the analysis of data sets, we may come across these types of data sets, and we may be able to see that these the conventional distributions that are available in the literature may not be able to describe the situation more appropriately, so that you may be able to look for some alternatives. And this is in an old data set that is available in Biometrica, and it is very well used by a number of researchers. And it is in fact the intervals in days between 109 successive coal mining disasters that has happened in Britain during the year 1985 to 1951. 1875 to 1951. 1875 to 1951, and this data set is very well examined by a number of researchers over the years from 1952 onwards. And you just look at the histogram of this. You can see that amazingly or surprisingly, you can see that the histogram behaves like this. You can see that in if you are looking, if I am taking it as some gap, it is like this, then 0 to let it be 200, you have a length like this one. 200 to 400, you have some other thing. 400 to 600, it is very little, and from 600 to 800, it is again little, and so there is some gaps between 1000 and 1200, and so. So, which is the distribution that you know in the literature are appropriate for modeling? So these are the questions that are of importance, not for us, but for practitioners. So in other words, this will in fact motivate us to give a deeper insight into the modeling of statistical data sets and the related distribution. And now, one of the mathematical tools that will help us to study the behavior of the distributions is the completely monotone functions. Now, let me look for the definition, the formal definition of complete monotonicity, which I will come later. So, just you look at a function phi that has the property that minus 1 raised to n into d lambda raised to d raised to n by d lambda raised to n phi lambda, that is minus 1 raised to n into the nth derivative of phi lambda is positive for n is equal to 1, 2, 3, etc. What does it mean? So when you put your n is equal to 1, what does it mean? Minus 1 into the first derivative is positive, which means that the first derivative itself should be negative. So the first derivative, if this is the definition, it means that the first derivative of phi should be negative. And what happens to the second derivative? So whenever n is 2, you may get minus 1 square, d square d lambda raised to 2, phi lambda is positive, which means that the second derivative should be positive. Similarly, the third derivative, you can see that it should be negative. Fourth derivative, it is positive, and so on. So you may have a function phi lambda, which has the property that the first derivative of it is negative, second derivative is positive, third derivative is negative, fourth is positive, and so on. So such a function I may call as, or we may call in the literature as, completely monotone function. Can you see an example for this function? So, okay, you can see a number of examples that I will show. So just look at this. Phi lambda is equal to lambda raised to alpha minus 1, where 0 less than alpha less than or equal to 1 and lambda greater than 0. So what does it mean? So you can see that what is its first derivative? First derivative is, in the first example, your phi lambda is lambda to the power alpha minus 1. First derivative is alpha minus 1 lambda to the power alpha minus 2. So alpha minus 1, since alpha is a quantity between 0 and 1, alpha minus 1 is negative, so that the first derivative is negative. The second derivative is alpha minus 1 into alpha minus 2, lambda to the power alpha minus 2, and you can see that, what is it? You can see that it is again positive. That is, alpha minus 1 is negative. So for that, you may have to restrict your alpha not between 0 to 1, 1 inclusive. You may have to restrict it is in the open interval 0, 1. So whenever your phi lambda is lambda to the power alpha minus 1, and alpha varies in the interval 0 to 1, you can see that your phi lambda has the property that it is the first derivative is negative, second derivative is positive, third derivative is negative, and so on. And now you look for that. Second, phi lambda equal to e raised to minus lambda to the power. If you just find the derivative of it, you can again see that it has its derivatives is of this nature. The first derivative is negative, second is positive, third is negative, fourth is positive, and so on. Right. Now you just look for the third example, that is 1 by 1 plus lambda, where lambda greater than 0. 1 by 1 plus lambda, lambda greater than 0. What does it mean? The first derivative is minus 1 into 1 plus lambda raised to minus 2, that is negative. Second derivative is positive, third derivative is negative, and so on. That is again completely monotone. And similar is the case of phi lambda is equal to 1 by lambda. So that is right. So this. So what is the role of these functions? That is, the function with the successive derivative has the property that the first one is negative, second is positive, third is negative, and so on. Is in the study of distribution theory. So this encounters, that is the completely monotone function encounters in distribution theory through Laplace transform. So through Laplace transform. So we have studied a number of transforms that are useful for studying the behavior of the corresponding functions, which may be either probability density function or distribution function, or in general may be any function associated with the given function. That is, you may be able to study the behavior of the distribution, and the study of the behavior of the distribution directly is somewhat, it may be difficult in some situations. So you may be able to look for some alternatives or some transforms which will in fact has the capability to describe the behavior of the given function in a unique manner. And we also, it is somewhat compatible in the sense that the further algebraic treatments are possible for the corresponding transform. So one such transform is nothing but it is the, so we have found a number of transforms like that. That is, one is the characteristic function, the other one is the moment identity function, and one which we will deal in the case of positive value random variables, is the random variables on Laplace is Laplace transform. So suppose you have your f is proper, or it may be a defective distribution on 0 infinity. If f is such a distribution, then the Laplace transform of f is given as or defined as integral 0 to infinity e raised to minus lambda x dfx, where lambda greater than or equal to 0, or in fact it should be such that the real part of lambda should be greater than 0. And you can see that this integral always exists. Provided always exists, and this will uniquely determine the phi lambda uniquely determines f, or there exists a one-on correspondence between your phi lambda and fx. So that correspondence will help you to identify the behavior of your fx through phi lambda. So this will help one to study the behavior of fx through phi lambda. So you may know, or you have studied in your, we have studied in our earlier classes. So being a workshop, I am looking for going for the elementary situations, and after that we will look into some of the recent results in distribution there. So my lecture is designed in such a way that at first we will discuss the elementary aspects of completely monotone functions and Laplace transforms, and why we need this in the study of distributions, and then we will look into the applications of this in the study of distribution theory. That is why the lecture is designed. So if your capital Fx has the derivative small fx, that is, if fx is x raised to a, then you can see that your phi, it is not x, phi of lambda is gamma a plus 1 by lambda raised to a. So you can see this. So, or in other words, you may be able to study the behavior of your fx equal to x raised to a through this phi lambda, which is equal to gamma a plus 1 by lambda raised to a plus. And if your fx is e raised to ax, then you can see that your phi lambda is 1 by lambda minus a, where lambda greater than a greater than 0, and you can see that it will diverge for lambda greater than or equal to. And similarly, you may have this e raised to, so suppose you have fx is equal to e raised to minus x square, then also you may not be able to evaluate this properly. And if you may see, similarly in the case of momentum function, you can find the derivative moments provided that the function phi, I am assuming that it is differentiable, and the derivative exists in the neighborhood of the origin. If the derivative exists in the neighborhood of the origin, then you may be able to find the expression for moments through the derivatives of phi lambda. And also, you may be able to study the behavior of the distribution function itself based on your phi lambda, because the integral 0 to infinity e raised to minus lambda x fx dx is nothing but phi lambda by lambda. And if you look for the transform of the survival function, it is 1 minus phi lambda by lambda. So based on the function 1 minus phi lambda by lambda, I may be able to study the behavior of the survival function corresponding to capital Fx, that is 1 minus fx. I may be able to study the behavior of my survival function based on this 1 minus phi lambda by lambda, or in other words, phi lambda. Based on phi lambda, I may be able to study the behavior of the distribution and the survival function in turn. And this is in fact the well-known result by Weinstein, which is known in the literature as the Weinstein theorem. That is, a function phi on 0 infinity is the Laplace transform of a probability distribution, if and only if it is completely monotone and phi 0 is 0. So, if you have a function phi which is completely monotone, what does it mean? Which means that its first derivative is negative, second derivative is positive, the derivative is negative, and so on. That is, your function is like that. The derivative nature is like that. And at the same time, the value of the function evaluated at 0 is 1. Then there corresponds a distribution corresponding to the for this phi lambda. You just look at the functions that we have considered earlier. We have considered earlier, and we have seen that these functions are completely monotone functions. We have completely monotone functions. But that is phi lambda equal to lambda raised to alpha minus 1, 0 less than alpha less than equal to 1, and lambda greater than 0. So is this the Laplace transform of probability distribution? The answer is no. Why it is so? Because phi 0 is not equal to 1. Now what happens in the second situation? You may have phi lambda equal to e raised to minus lambda raised to alpha. You can very well find the derivative of it, and you can see that its nature is the first derivative is negative, second derivative is positive, and so on. And at the same time, so that it is completely monotone, and also at the same time phi 0 is equal to 1, which will in fact tell you that this phi lambda is the Laplace transform of a probability. So it is the Laplace transform of a probability distribution, and you know that that is nothing but it is the positive stable law that we may study in the literature, or we may use in the literature, which is very well, that is a stable distribution with exponent alpha, where alpha we are restricting in the 0 to 1, and you can see that whenever alpha equal to 1 by 2, you may be able to find exact expression for the corresponding distribution functions, which is in fact connected with what is the inverse Gaussian distribution. That is, that very well one may be able to see. And the third one is where phi lambda is equal to 1 by 1 plus lambda. 1 by 1 plus lambda, phi lambda is equal to 1 by 1 plus lambda. What does it mean? What is it? In that case also you can see that it is completely monotone, and also your phi 0 is equal to 1. So phi lambda equal to 1 by 1 plus lambda is the Laplace transform of a probability. And that you know that it is nothing but it is the exponential distribution. The unit exponential distribution, the Laplace transform of the unit exponential distribution is nothing but phi lambda equal to 1. Or in other words, if you are not aware about that, you can find it based on the inversion theorem. So, or in other words, phi lambda equal to 1 by 1 plus lambda is the Laplace transform of a probability distribution based on the result that we have seen now. So this the result by Weinstein. So the function phi is the Laplace transform of probability distribution if and only if it is completely monotone and phi 0 is equal. And you can see that the last example that I have put there, it is not the Laplace transform of a probability. This phi lambda equal to 1 by 1 plus lambda, you can see that very well see that it is completely monotone, but phi 0 is nothing but it is infinite. So the phi lambda equal to 1 by lambda cannot be the Laplace transform of a probability distribution. Now, once the Laplace transform is given using the inversion formula, you may be able to find the corresponding function or corresponding function. And you know the inversion formula is nothing but it depends upon, as you expect, the derivative. And the function phi lambda on 0 infinity is completely monotone. If I leave that is what I have already told. That is where the Weinstein theorem itself. That is, if the function phi is completely monotone, if and only if it is at the form integral 0 to infinity e raised to minus lambda is dfx, and where f is not necessarily a finite measure on 0, not necessarily. And you may be able to define the various aspects of the inversion formula. And these are the other properties of it. That is, if you have two functions that are completely monotone, the derivative you can see the product of them, that you can see that it is again completely monotone. And also, you look at the reverse of this. So I have the formula that we have described earlier. That is this. That is minus 1 raised to n d raised to d by d lambda n of phi lambda is positive for n is equal to 1. That we may call it as completely monotone. And the derivatives is this. Now let me look for the other way around. That is minus 1 to the power n d by d lambda to the power n phi lambda is negative for n is equal to 1. Does there exist such a function? So if so, what is the relationship between these functions? That is the one that now we may try to investigate. So that is the one that we will now discuss. So that is the functions with complete monotone derivative that we will call it as this one. Minus 1 raised to n into d by d lambda n phi lambda or phi n lambda less than or equal to 0 for n is equal to 1, 2, 3, etc. You just put n is equal to 1. That is minus phi dash lambda is negative. Minus phi dash lambda is negative means that what is your phi dash lambda? Phi dash lambda should be positive. There should be no other alternative. So that is you may have n is equal to 1, you may have minus 1 into phi dash lambda is negative, which means that phi dash lambda should be positive. And whenever n is equal to 2, what is it? Minus 1 square into phi double dash lambda is negative, which means that phi double dash lambda should be negative. And similarly, the third derivative should be positive, fourth one is negative, fifth one is positive, and so on. So this is, we may call it as functions with complete monotone derivative. This we will call in the literature as the functions with complete monotone derivative. Just look at, as an example, just restrict your alpha, not in the interval 0 to 1, 1 included. It should be put as 0 to 1, 1 excluded. So you may have the phi lambda equal to lambda to the power alpha, alpha in the open interval 0, 1 and lambda positive. Just look at the derivative, the nature of the derivative. The first derivative phi dash lambda is alpha lambda raised to alpha minus n, it is positive. The second derivative is alpha into alpha minus 1, lambda raised to alpha minus 2. Since alpha is in the interval 0, 1, alpha into alpha minus 1 is negative. So that the second derivative is negative. Similarly, the third derivative has the coefficient term alpha, alpha minus 1, alpha minus 2. And being alpha in the interval 0 to 1, alpha minus 1, alpha minus 2 multiplied with alpha is again is positive. So the third derivative is positive, fourth derivative is negative. So that is what you have here. So if I is completely monotone and psi a positive function with a psi a positive function with a complete monotone derivative, then phi of psi is completely monotone. So if phi is completely monotone and psi is Weinstein, then phi of psi is completely monotone. So you can see that e raised to minus psi is completely monotone. Okay. That is how you may prove that you can easily prove that your e raised to minus lambda to the power alpha is completely monotone. How will you prove that? That is your e raised to minus lambda, you can see that it is always completely monotone. No need, you can easily prove it. Because if you take e raised to minus lambda, the first derivative is negative, second derivative is positive, third derivative is negative, and so on. So that it is completely monotone. And if you put take your psi lambda as lambda to the power alpha, you can see that it is Weinstein. That is, it has CMD. It has complete monotone derivative. So, or in other words, the first derivative is positive, second derivative is negative, and so on. So, based on that, the result that we have now, you can very well prove that your e raised to minus lambda psi lambda, that is e raised to minus lambda to the power alpha, is completely monotone. Is completely monotone. You can very well see that your e raised to minus lambda to the power alpha is monotone. Now, you just look at some functions that you may come across in the literature. Some distributions that we will come in the literature. So let me consider phi lambda, which is such that it is completely monotone with phi 0 is equal to 1. And let me define g of x is equal to 1 minus phi x. My question is whether gx is a distribution function. So my phi lambda is completely monotone with phi 0 is equal to 1, which means that phi lambda is the Laplace transform of probability distribution. That is based on the theorem that I have already told. Already we have discussed that theorem. So now I may define gx is equal to 1 minus phi x, where phi x is the Laplace transform of a probability distribution. Then my question is whether gx is a distribution function. Now, what is the motivation for defining gx as 1 minus phi x? We just look at some of the distributions that you know. That is, my question is g a distribution function? Second one, if so, is it has complete monotone derivative or is g completely monotone? Or a function with a complete monotone derivative is itself a distribution function, can itself be a distribution. We just look at some of the examples that you know that if you take your phi x is equal to e raised to minus x, is it Laplace transform? If phi x is equal to e raised to minus x, you can see that it is the Laplace transform of a dependent random variable. So, right. So in this one, you may be able to see that it is equal to this. And now your gx is equal to 1 minus e raised to minus x, x greater than 0, and you have studied it in the literature as the distribution function, not exponential. So we have got gx is equal to 1 minus e raised to minus x, and we have very well studied in the literature as the distribution function of the exponential random variable. Unit exponential random variable is 1 minus e raised to minus x, and which I may be able to view as a mathematician, we may be able to view as it is equal to 1 minus e raised to minus x, where phi x e raised to minus x is itself a completely monotone function. Now you just look for the other. Suppose my function phi x is equal to e raised to minus x to the power alpha. And if you take gx is equal to 1 minus e raised to minus x to the power alpha, you have already studied it. The gx is again a distribution function. And which you may call it as the Weibull distribution. In the literature, in the statistics literature, we may call it that. And you can see that e raised to minus x to the power alpha, that is again a Laplace transform. Right? That which is nothing but it is the Laplace transform of stable random, positive stable random variable. When my alpha is, I am restricting the interval 0 to 1. And you can see that I am talking all these things in based on the Laplace transform. And so the existence of Laplace transform is guaranteed, so that you may, for that you may be able to restrict your alpha to the interval 0 to 1. Now you look for the Pareto distribution that you have. The Pareto distribution, you may be able to write it as gx is equal to phi x is equal to 1 by 1 plus x, x greater than 0. Phi x is equal to 1 by 1 plus x, x greater than 0. Then what is the corresponding distribution function gx? Gx is equal to 1 minus 1 by 1 plus x. And I have already showed you that 1 by 1 plus x is a Laplace transform. That is, it is completely monotone and its value at 0 is equal to 1. So it is a Laplace transform, and if you define gx is equal to 1 minus 1 by 1 plus x, that is, you have studied in the literature as the Pareto type 3 distribution with parameter 1. So that is again a distribution function. So if I may take g is equal to 1 minus phi x, where phi x is itself a Laplace transform, then I am getting that gx is again a distribution function. Right. So that is this that you may be able to see in the framework that we have described so far. And now you just look at the structure of the derivatives of gx. Gx, you are looking for the derivatives of the Gx. Gx, if you look for the derivative of Gx, you can see that Gx is nothing but, since phi is completely monotone, and you can see that the minus 1 raised to n, d raised to n by d lambda raised to n phi lambda should be positive. And based on that, you may get your Gx as complete monotone derivative. Gx is a function which has complete monotone. Gx is a function with complete monotone derivative. So, or in other words, the Gx will define a class of distributions which we will call in the literature, or it is known in the literature as distribution with complete monotone derivative. It is known in the literature as distributions with complete monotone derivative. And you can very well prove that in a distribution with a complete monotone derivative, that is your exponential or its variable or Pareto and so on, you may be able to represent it as a mixture of exponentials. And there is a well-known theorem in the literature that a function or a distribution has complete monotone derivative if and only if it is a mixture of exponentials. You can very well prove it. I'm not looking for going for the proof of it. So these things, these notions will tell us that there is some connections with the distributions with complete monotone derivative and also the completely monotone functions and the statistical probability statistical distribution. There is some connections between these two. And there are some other equations that you can see in branching process. And you can see that if you look for the structure of completely monotone functions, you can see that a completely monotone function that I am assuming that it is positive. You can see that it is a decreasing function and convex. And the set of all completely monotone functions is a convex cone containing the positive constant functions. And we have already discussed that the product of any two completely monotone functions is completely monotone. And a Weinstein function is again positive, but it should be the other way around. That is, it is being complete monotone derivative, it is increasing in curve. And the structure of convex cones of completely monotone functions and Weinstein functions, and the relationship between these cones resemble the structure of convex cones of positive definite and negative definite functions, and the relation between these two cones that you may be able to see in the literature. And now I may go through the role of these completely monotone functions and functions with complete monotone derivative in defining infinite divisibility property, infinitely divisible probability distribution. Now, the infinitely divisible distribution, that is a class of distribution that is well known in the literature, and it arises in the study of limit theorems and also study of convolution semigroups. You can see that the class of all continuous convolution semigroups will coincide with the class of all infinitely divisible distributions. And also you may be able to represent the class of all infinitely divisible distributions as the limit of Poisson type distributions or Poisson type characteristic functions and so. And now what is the role of infinitely divisible distributions in the study of distributions as a whole? That is, if you are looking for the limit distributions as sums of independent random variables. So in the classroom setup, we may come across that is under finite variance we have the limit law may be normal. So if you may relax the concept of finite variance, you may be able to get a larger class that may contain the normal law, which you will end up with the class of stable laws. And further relaxation when you are making it, and you are assuming that the random variables are such that they are not independent in general, but you are assuming that the random variables in the rows are independent. The random variables are row-wise independent. In the rows, I am not assuming. The random variables are row-wise independent. You may arrive at what is known as the self-decomposable distributions. That is the random variables that may be able to, you may be able to divide it into two components, of which one will be exactly, or is one will behave same as the original component. So that you may call it as the self-decomposable random variable. So you may be able to find some random variable which you may be able to decompose into two, of which in the decomposed part, one component should be of the same type or exactly the same as the original component. And these decompositions are not admissible for all random variables. And the random variables, those decompositions are applicable only to continuous random, absolutely continuous random variables. And the class that is known in the literature as the class of self-decomposable distributions. And if you realize the assumption of row-wise independence again, then the limit law will coincide with the class of infinitely divisible distributions. Or in other words, what is the role of infinitely divisible distributions? Is it appears as the limit distribution of sums of random variables, so independent random variables under some settings, and also the infinite divisibility property. What does it mean? It means that you may be able to divide the random variable into infinitely many components, and that division is its division help one to find the corresponding stationary distribution, describe the existence of the stationary distribution by stochastic. Or in other words, when the random variable is infinitely divisible, you may be able to construct a corresponding stochastic process or a random process. So where you may be able to define, suppose I have asked you to define an exponential process, exponential stochastic process, or I have asked you to define an inverse Gaussian process, or I have been asked you to define a geometric process. So first of all, I will check whether the random variable is infinitely divisible, and if it is infinitely divisible, based on that I may be able to define the corresponding stochastic process. So the infinite divisibility property enables one to construct the corresponding stochastic process. And so in the study of random processes and in the study of limit theorems, the class of infinitely divisible distributions is a major role. And you may be able to study the behavior of infinitely divisible probability distribution and its Laplace transform based on completely monotone functions. So or another, that is what's my aim. So let me look for this definition. The function phi is the Laplace transform of an infinitely divisible probability distribution. If and only if phi is, you may be able to write it as e raised to minus psi, where psi has complete monotone term and psi 0 is equal to 0. You just look at an example that you have seen. You just write your phi is equal to e raised to minus lambda raised to alpha. And you can see that lambda raised to alpha, I have taken psi lambda as lambda raised to alpha. Lambda raised to alpha is a function that has CMD, complete monotone derivative. And what is psi lambda is lambda raised to alpha, so that psi 0 is 0. So psi has complete monotone derivative, psi 0 is 0. So my phi equal to e raised to minus lambda raised to alpha is the Laplace transform of an infinitely divisible distribution. Infinitely divisible distribution, so that is you may be able to study the behavior of that. And you can see that if your phi is infinitely divisible, then you can maybe be able to write it as phi is equal to e raised to minus psi, where psi you may be able to write it as integral 0 to infinity 1 minus e raised to minus lambda x by x p dx, where p is a measure such that integral 1 to infinity p dx by x is finite. So, what is the role of this? What is the use of it? So, use of it is that this P we will call it as the spectrum function associated with the infinitely divisible distribution having Laplace transform phi lambda. So P is known in the literature as the spectrum function corresponding to the infinitely divisible distribution having Laplace transform phi lambda. Okay. So there exists a unique relationship between phi and P. Or in other words, you may be able to define or identify your distribution associated with your phi lambda from this P. Just look at this example. Suppose fx is you have the gamma density, x raised to a minus 1 e raised to minus x by gamma here. Then you find its Laplace transform. So it is phi of lambda, that is not phi of x, that is you may be able to write it as 1, if you find it, you may be able to get it as 1 plus lambda raised to lambda plus 1 whole to the power a. That you may be able to write it as e raised to minus psi lambda. So what is psi lambda? Psi lambda is minus a logarithm of lambda plus 1. And if you find the corresponding integral representation of that one, you may be able to find that you can write that psi lambda as integral 0 to infinity 1 minus e raised to minus lambda x by x pdx. And what is the pdx? You may be able to identify the corresponding pdx. Okay, like this. Now I will look for some of the distributions that one may be able to study or develop or look for the further research that is developed in the literature, which is known as the Metcalfe distribution. I may just look for some of its origin, how it was developed, the development and history and development of the Metcalfe distribution, which is nowadays used in a number of branches in other disciplines, that is in physics, in astronomy, and so on, in various branches of science. For example, in finance, for modeling heavy-tailed data sets and so on, is the well-known Metcalfe distribution. So for that, how this distribution was evolved, what is the logic behind in developing this distribution. So this distribution was in fact developed by Professor R.N. Pillai in 1990, in early 90s, based on the concept that I have described so far. It is based on the property of complete monotonicities, completely monotone functions and functions with complete monotone derivative. And you can see that the Metcalfe distribution that we will now popular in the literature is derived from the properties of completely monotone functions, and the distribution function itself you may be able to see, that is, it is well established by Lin in a series of papers which appeared in Journal of Mathematical Analysis. He has proved that it is a function with complete monotone derivative itself. It is a distribution with complete monotone derivative itself. So now let us look for the function. Let us look for a function phi lambda, which is equal to 1 by 1 plus lambda raised to alpha, where I may just restrict alpha over the interval 0 to 1. And I will just check whether it is completely monotone. Phi alpha lambda, which is 1 by 1 plus lambda raised to alpha, is completely monotone with phi alpha 0 is equal to 1. You can very well see that phi alpha evaluated as 0 is clearly equal to 1. And now my question is whether phi alpha lambda is completely monotone. If it is again, it is also satisfied by the result due to Bernstein, I may conclude that, or I may think that intuitively we may be able to think that there may be a probability distribution that has the Laplace transform 1 by 1 plus lambda. So, so let us check whether 1 by 1 plus lambda raised to alpha is completely monotone. For that, let me take phi lambda is equal, let me take a function 1 by 1 plus lambda. 1 by 1 plus lambda, you can see that it is completely monotone. And lambda raised to alpha, we have already seen that it has complete monotone derivative for alpha in the theorem. So you have a function that is you have, let me have this one, you have a function phi lambda which is equal to 1 by phi alpha, not phi alpha lambda, I am simply saying it as phi lambda. Phi lambda is completely monotone, and also phi lambda is equal to 1 by 1 plus lambda is completely monotone. That is, its first derivative is positive, second derivative negative, and so on. And so the first derivative is, its first derivative is negative, second derivative is positive, and so on. And also, psi lambda, which I am taking, it is lambda raised to alpha. It has complete monotone derivative, which means that the first derivative is positive, second negative, third derivative positive, and so on. And if phi lambda is completely monotone and psi lambda has complete monotone derivative, then the result that we have already established, already seen, you can see that phi of psi lambda is completely monotone. That is, phi of psi lambda is, what is it? Phi lambda is 1 by 1 plus lambda raised to alpha. Psi lambda itself is lambda raised to alpha. So, what is the value of phi evaluated at psi lambda? The value of phi evaluated at psi lambda, which is equal to lambda raised to alpha, is phi of lambda raised to alpha, which is 1 by 1 plus lambda. So that result is that your 1 by 1 plus lambda raised to alpha is completely monotone, and also its value at 0 is equal to, at 0 is 1. So the Weinstein theorem tells that there should exist a probability distribution whose Laplace transform is this 1 by 1 plus lambda. Now the next natural question is, then what is that? If so, then what is the corresponding probability distribution? You can see that your phi alpha lambda is equal to 1 by 1 plus lambda is the Laplace transform of probability distribution. So you just look at when you just put your alpha is in the interval 0 to 1. Now, when you put alpha equal to 1, you will get 1 by 1 plus lambda. What is it? It is the Laplace transform of exponential. So, you may see that this will lead to be a class of distribution which may contain, which in fact contain the exponential distribution as a special case for lambda equal to 1, for alpha equal to 1. So, this is a generalization of the exponential. So now our aim is, what is the corresponding distribution? How will you find it? So you may be able to use the inversion theorems, and the inversion theorems you may be able to do it, but it will take a lot of time, and it is not mathematically, it is very difficult. But for that, but if you look for the textbook by Feller, that is the concept that I am discussing here is mainly based on the textbook by Feller Volume 2. Feller Volume 2, there is a chapter on applications of Laplace transforms, that is the Laplace transforms and its applications mainly on defining or discussing Tauberian theorems. So, and also so in that connection you may come across what is the Karamata's extension theorems and so. So that you may be able to see in the Feller's book. So, for a better understanding of what the things that I have discussed so far, one who is interested may read the textbook by Feller, and also some of the things that I have discussed, what I discuss later, they may not be available in the literature. It is spread over some journals and so on. Research articles. So the matter that I have discussed is over, one will be able to, for a better understanding of it, one may be able to refer to the book by Feller Volume 2. And as I know that what happens whenever your alpha equal to 1, when alpha equal to 1, you may get it is 1 by 1 plus lambda, it is unit exponential. Phi alpha lambda is equal to Then the phi 1 lambda is unit exponential, then what is phi alpha lambda? Sadish? Hello? The Professor Sadish, can you hear me? Professor Sadish? Whether I may have to continue it, whether Professor Kalyan sir, whether Professor Kundu has joined or not? Whether Professor Kundu has joined?
Huh?
Whether Professor Kundu has joined, sir?
So he will be presenting?
Whether Professor Kundu has joined, that I want to know that one. That is what I want to see whether I may have to continue or whether he is joining.
I think since you have started, there are.
Okay, I will continue, sir.
You continue, let
Okay.
it be decided by the authorities.
Okay. You can see the screen now. Is it okay, sir? The screen is visible. Yes.
Yes, sir. Yes, sir.
So, this here phi 1 lambda is 1 by 1 plus lambda. That is, you can see that it is unit exponential. Now, so now the next question is, what is our phi lambda? Is it naturally, intuitively, one may think that it may be a generalization of the exponential distribution. So for that, this is a function that is described in the Fellier's book that you can read there. That is the function is E alpha Z, which is 1 by 2 pi I integral over C t to the power alpha minus 1 e raised to t divided by e raised to alpha minus Z dt, where the path of integration capital C, it is a complex integral, that is, C is a loop which starts and ends at minus infinity. That's in the usual contour that you have. And at the same time, it encircles the circular disk. That is, where the value of t lies in the interval minus z to the power 1 by alpha and z to the power 1 by alpha. And at the same time, you can see that your E alpha S is in fact an additive function, that is an entire function of order 1 by alpha greater. So this is a function that you can see in the Fellier's book, and it is the origin of this function is the function was introduced in another context, in a very different context by Mithagliffer in 1903. And the Feller has found in the book that you can see the value of that E alpha Z. E alpha Z, one you may be able to evaluate it through contour integration, and you can see that you may be able to write your E alpha Z as sigma over k is equal to 0 to infinity Z raised to k by gamma 1 plus k alpha. That is the value of this. That is the value of this complex integral that is an infinite series. And this function later on found has, that is by looking at the various structures and so on, that has found later, that we will come to later. So you can see that this 1 minus E alpha minus x to the power alpha, that if you find 1 minus E alpha evaluated at minus x to the power alpha, you just substitute in place of this z, E alpha z. If I may replace this E alpha z, which is represented as the infinite series, if I am replacing it by minus x to the power alpha, then the Laplace transform of 1 minus that is nothing but 1 by 1 plus lambda raised to alpha or t raised to alpha, whatever it is. That is this. That is proved in a paper by Professor Pullai, which appeared in Annals of Institute of Statistical Mathematics, Annals of Institute of Statistical Mathematics, Annals of Institute of, not Mathematics, it's Statistical Mathematics, in the Japanese journal. So, your E alpha minus z to the power alpha, E alpha minus z to the power alpha, 1 minus of that, if you find the Laplace transform of it, you can see that it is nothing but 1 plus t to the power alpha. You can clearly find it out very well. That is, you just define, this is the function. This is your f alpha x that you are getting. If you find the integral of this one, you may be here, you can see that the 10 by 10 integration is possible. You can see that since the sum is converged, then you may be able to integrate the 10 by 10, and so you you may be able to find the Laplace transform of sigma over k is equal to 1 to infinity minus 1 to the power k minus 1 x raised to k alpha by gamma 1 plus k alpha. That the Laplace transform of that is nothing but it is 1 by 1 plus t to the power alpha, or 1 by 1 if it is evaluated lambda, 1 by 1 plus lambda raised to. So you can clearly see just simple simplification will lead you to this function. So the function f alpha x is equal to sigma over k is equal to 1 to infinity minus 1 to the power k minus 1 x raised to k alpha by gamma 1 plus k alpha. 0 less than alpha less than or equal to 1 is the distribution function which is associated with the Laplace transform 1 by 1 plus lambda raised to alpha. So 1 by 1 plus lambda is the Laplace transform of exponential distribution, or the distribution associated with the Laplace having the Laplace transform 1 by 1 plus lambda is exponential, whereas the distribution as having Laplace transform 1 by 1 plus lambda raised to alpha is the one which has the distribution function sigma over k is equal to 1 to infinity minus 1 raised to k minus 1 x raised to k alpha by gamma 1 plus k alpha. There I may restrict alpha in the interval 0 to 1. Why I have to restrict alpha in the interval 0 to 1? What happens here when alpha is greater than 1? Whenever alpha is greater than 1, you can see that the phi lambda is no longer a Laplace transform. It is no longer a Laplace transform. Phi lambda ceases to be a Laplace transform for alpha greater than 1. So I may have to restrict my alpha, the parameter alpha, over the range 0 to 1, including 1. So that's now. So this is the corresponding density. I can see that this function is in fact the series is convergent, and you may be able to define the density itself by simple differentiation. So this is the Laplace transform. If you find the Laplace transform of this one, you may be able to find the Laplace transform of this directly, and you can see that it is nothing but this one being lambda to the power alpha. Now, okay. you can find the distribution function of this one. You can see that these things are developed in Kerala University, and Professor Kalyanam sir was in fact he made a crucial role in developing at that time the computer. The work, this work was done in early in 1990s, about 1988, 90s, and so on. So in that time, Professor Kalyanam sir has helped in deriving most of the properties of these distributions using the computers and programming, computer programs and all. And now I remember when Professor Sabu Jor, etc., who are worked in the earlier days on the properties of the Michael functions and Michael distributions, and in general the distributions that are normally attracted to stable. So you may be able to generalize this class, the class of distributions that we are discussing now, to the class of distributions on R plus that are normally attracted to stable. When you say that the class is normally attracted to stable law, so you may have, you are restricting the normalizing constant as 1 by n to the power 1 by alpha, where alpha is in the interval 0 to 1. So then we know the classical limit theorems and all that, and in the classical limit theorems, when you are restricting your normalizing constant, that is the scaling constant, as 1 by n to the power 1 by alpha, and alpha is in the over 0 to 1, you may get the class of distributions that are normally attracted to stable law. You may be able to generalize this to that situation also. Okay. And so after the introduction of Michael distribution in the literature, a lot of works has appeared in the literature on various properties of this distribution. So why this distribution is so instrumental, or why this has so many properties, or what are the hidden properties that are, what are the additional properties that this distribution possesses as compared to the well-known exponential and the other distributions that are available in the literature. So what is its importance? So if you look for the literature, if you look for the history of distributions and the history of limit theorems. For example, you may be able to study read the book by Random Summation by Krugolov. So you can see that in the Russian school, they have in fact discussed in some way or other these types of functions, but they may not be able to arrive derive the corresponding distributions and so on associated with this function. So you can look into for a detailed understanding, we may be able to look into the book by the Krugelov's book on random summation theory and applications. So in that, we may come across some data sets where the data sets behaves in such a way that you may be able to model the distributions based on the exponential law, where the probability content in that tail area is dominant as compared to the exponential. So when we say that a distribution is heavy tail, so we have a distribution, we have studied a class of distribution, a number of distributions in the literature based on the behavior of the tails. That is, one is the fat tail distributions, heavy tail distributions, long tail distributions, class of distributions with dominator variation tails, and the class of sub-exponential distributions, and so on. So when one is looking for the extremes and all that, or the studies of extremes and insurance risks and so on, we may come across the class of distributions that I have named so far. That is the heavy tail distributions. So the heavy tail distributions are those whose tails are heavier than that of the exponential distribution. That is the definition available in the literature for heavy tail distributions. And you just look at the behavior of this function that you can see that if your alpha is equal to, this is the distribution function. So you may be able to think of, I haven't plotted the density function, I have given the density function here also, you may be able to think of the density function based on this. So what happens whenever alpha equal to 0.3? Alpha equal to 0.3, the probability content in the tail area is more compared to alpha equal to 0.5. If the probability content in the tail area is more compared to 0.7, probability content in the tail area is more compared to 0.9, and the probability content for alpha equal to 0.9 is more as compared to the probability content at 1. So, or in other words, the exponential distribution you may be able to view it as a light tail distribution, or the one that you may be able to find the boundary. You can see that there are situations where the tail area is dominant, and the tail area is dominant such a behavior you may be able to model satisfactorily using this distribution. And there are a lot of situations that are identified by not by statisticians but by the persons in other areas, and they have found that this distribution is applicable in such for modeling their situations. Then let me look for some of the applications they have noted. Before that, let me look for some of the properties of this distribution function. The distribution function is this one. So you just look for alpha equal to 1. If alpha x is equal to sigma over k is equal to 1 to infinity minus 1 raised to k minus 1 x raised to k alpha by gamma 1 plus k alpha, where 0 less than alpha less than or equal to 1. What happens when alpha equal to 1? That is your f1x. f1x is equal to sigma over k is equal to 1 to infinity minus 1 raised to k minus 1 x raised to, I am restricting alpha as 1. That is x raised to k by gamma 1 plus k. So, or in other words, your f1x is sigma over k is equal to 1 to infinity minus 1 raised to k minus 1 x raised to k by k factorial, and because gamma 1 plus k is k factorial, and I am assuming that my k is an integer. So it is k factorial. If you simplify it, what does its value? It is 1 minus e raised to minus x. That is sigma over k is equal to 1 to infinity minus 1 raised to k minus 1 x raised to k by k factorial is 1 minus e raised to minus x. So that is why you will we are calling that f alpha x is a generalization of the classical exponential distribution. And also, what is the behavior of f alpha x for various values of alpha as compared to f1x? You can see that whenever alpha decreases from 1 to 0, you can see that the tail of the distribution becomes more and more heavier or thicker. So the parameter alpha is nothing but it is the tail index determining parameter. It is the indexing parameter which determines the tail behavior of the function. And you can see that there are some functions in the literature which I have already named, that is heavy tailed functions. When you say that a function, a distribution is heavy tailed, or when you say that a function is heavy tailed, or when you say that a function is so the heavy tail phenomena and the functions of regular variations are well connected. I am not going into the details of it. If one is interested on these things, you may be able to read the textbook by Feller, and also there is a paper by Kluppelberg on the class of sub-exponential distributions and integrated tails, which appeared in the Journal of Applied Probability in the year 1988. There is a paper by Kluppelberg which appeared in the Journal of Applied Probability in the year 1988, where they are describing certain classes of distributions, which is one class is the class of sub-exponential distribution, the other one is the class of long-tailed distribution, the class of heavy-tailed distribution, class of distributions in class And when you say that the distributions are tail equivalent and so, there are a lot of concepts they are described, and they have proved a number of criteria to establish this property. And you can see that you may be able, some of the things are very well applied in the context of this distribution, the Pythagorean distribution, and that in fact makes the distribution. That is, you can see that the Pythagorean function or the Pythagorean distribution function. If you are looking for the tail of the distribution, the tail is in fact it has a regularly varying tail. It has a regularly varying tail. That is the property of that. It is that property that makes that this distribution applicable in modeling various types of financial data and other data sets. And now you can see that it is proved by Lin in a paper which appeared in Journal of Statistical Planning and Inference, that the Pythagorean distribution function, it has complete monotone derivative, and he has obtained the fractional derivatives corresponding to this. And the Pythagorean stochastic process was already proved in Professor Pillai, and he has proved some other properties and related properties corresponding to this by Professor Lin. And you can see that I have already told that the Pythagorean distribution is a distribution that is normally attracted to stable law, positive stable law. It is self-decomposable. It is geometrically infinitely divisible. And since it is infinitely divisible, every geometrically infinitely divisible distribution is infinitely divisible. And since infinitely divisible, it makes one to develop the corresponding stochastic process. So the corresponding Pythagorean stochastic process developed in the literature, and the construction of ML distribution is using this E function, that is using the Pythagorean function, that can be extended in a number of manners, and that construction was extended by Fujita to derive the characterizations of geometrically infinitely divisible distributions. So the construction mechanism through the Pythagorean integral, you may be able to analyze it, and you can read the textbook by Fujita in the paper by Fujita in Analysis Institute of Statistical Mathematics. That the paper is in fact titled as a generalization of the results of Professor Pillai. A generalization of results of Pillai. That is the title of that paper. So that in fact tells how the Pythagorean distribution can be generalized to derive the geometrically infinitely divisible. And also, Lin in fact characterized the Pythagorean distribution through the spectrum function of infinitely divisible distribution. That is, the Pythagorean distribution is in fact the Pythagorean distribution is in fact the Pythagorean distribution is in fact infinitely divisible. So since it is infinitely divisible, I have already proved that there is a result that connects infinite divisibility and spectrum functions of infinitely divisible distributions. So we may be able to characterize the distributions through spectrum functions of infinitely divisible distributions. So based on that, myself and Professor Pillai, we have proved a number of characterizations of Pythagorean distributions, and these characterizations are extended by Professor Lin in a paper which appeared in Australian and New Zealand Journal of Statistics. And this Pythagorean distribution is applied in a number of contexts. One is the random stability in a paper which appeared in Analysis of Probability by Professor Bunch. And the Pythagorean distribution is applied for deriving or studying the cold relaxation phenomena by the physicists Veron and Kotulski in a paper which appeared in Physica A. Statistical mechanics for describing the core relaxation phenomena in mechanics. And also, it is applied to derive closed form representation of kinetic equation and thermonuclear function in a paper by Hobbold, which appeared in Hobbold and his team appeared in Journal of Applied Mathematics. And also it is applied, the methyl distribution is applied in identifying and describing sunspot number problem. And Nissan has applied it, in fact, in describing the nature of rate of flow of water in a Kallada river in Kerala, in a paper which appeared in Mathematical and Computer Modeling. And also, it is the count model based on Mittag-Leffler interarrival times. The Mittag-Leffler is being a generalization of exponential. You may think of the corresponding interarrival times and the corresponding queuing network. Right. If the interarrival times are exponential, the corresponding arrival pattern is Poisson. That is very well known in literature. So one may think, suppose the interarrival times are Mittag-Leffler, then what is the corresponding the arrival pattern? That is one of the topic of very catching interest. And Jose and Bindu has proved that, and they have derived the corresponding count model associated with the Mittag-Leffler interarrival times. And it has a number of nice properties. And the applications of the Mittag-Leffler distributions and its real counterpart, that is the linear distributions or alpha Laplace distribution, which was studied by myself, Professor Pillai and Professor Kalyan Rama, they are very well reinvestigated and re-examined by Professor Rachev, Professor Kusubowski and their team. And they have applied it in a number of contests, that is in financial modeling and daily stock returns, commodity price, exchange price, commodity prices, foreign currency exchange rates, etc. And we can see that the Mittag-Leffler distribution and its real counterpart are very well used for, can be very well applied for describing more efficiently the data sets appearing in these areas. Now I am looking for some functional equations that are leading to this one, that I am not going into the details. So let me stop here. The time is about over 1.5 hours. And so I think that I have 77 slides. I am not going into all the details. So that will in fact describe the remaining section that I may be, what I was looking for was the integral equation, how the generalizations of exponentials are possible. One generalization I have told. One generalization I have told through the Laplace transform. And one such generalization is the Mittag-Leffler distribution. Now, the exponential distribution, one may be able to view from another angle, which is that angle that is from the functional equation point of view. You can, whether the exponential distribution or exponential distribution arises as a solution of a functional equation, yes, of course. So the students, as a student, we have studied it. That is, when we are deriving the lack of memory property, we can see that the exponential distribution or the corresponding density, we will get it as the solution of a function. So a natural question is, that is, if you generalize that functional equation, you may get a generalization of the exponential law. So then what is that generalization? So these are the things that are in the next parts of my discussion that I am not going to do in the details. If one is interested on it, one may be able to look for this. That is the simple Cauchy functional equation. That is, you have this one, fx plus y is equal to fx plus fy. The solution is x and you have fx plus y is equal to fx into fy. You can see that it is e raised to x, and you can see that if you are looking for the exponential distribution. So in the lack of memory property we are looking for, we are arriving at the functional equation this time. Now this is the generalization of that. It generalizes that is viewed in the literature as what is known as the integrated Cauchy functional equation, and the integrated Cauchy functional equation is very well established, very well examined by Professor C.R. Rao and his team, and you can see that a number of combined papers by Lau and Rao on the integrated Cauchy functional equations and its applications and its need in deriving a lot of real life phenomena more realistic. So, and the generalizations are also possible. Kundu has derived another generalization of exponential, which now known in the literature as the generalized exponential distribution, and so on. There are a number of generalizations are available, and okay, well, another one is the Marshall-Olkin generalization of exponential distribution, which is in fact based on the scheme of random minimization of a random minimum of a random number of random variables, minimum of a random number of random variables, where one can see that such a situation will arrive more realistically. And also, there are some situations where we may come across is nothing but the one that is described by Professor Tom Kusubowski in the yesterday's talk, where he has described on transmuted laws, transmuted distributions, and the transmutation map. That is a transmuted generalization of exponential will in fact be a will leads to another generalization of exponential. So all those things are generalization of the same distribution, that is one distribution. Why it is so? The answer to that I have already answered in my earlier from the very beginning. That is, if you are looking for, if you are an experimenter, and if you are rely upon your data sets, and you can see, you may see that the distributions that are available in the literature may not be capable to describe the realistic situation more appropriately. And so one may be able to need more and more alternatives, effective alternatives, to describe the exact situation more appropriately. So with this, let me conclude. Thank you all, and any questions or comments, please.
Kundu's mail now, thank you, Jayakumar. Now anyone can any questions or doubts or comments, suggestions, you can respond, please. Or you can put in the chat box also, no problem.
Nice. Nice presentation, Jayakumar. Very happy to hear about Metagala for a very long time.
Thank you, sir. Thank you, sir.
Why people are not talking about the distribution? Supposed to be having a lot of say what we call potential in it. Opportunity for exponential distribution with a longer tail. And do you remember one characterization? I don't remember that with the stable distribution with ML.
There is a characterization based on stable laws. There are characterization based on stable laws and with Taylor distribution.
No, there is one characterization.
Yeah.
Connecting stable distribution and some other distribution.
If I E is exponential and y is stable, then e raised to 1 by alpha y is beta.
Please repeat it. Please repeat it. Please repeat it.
Yeah. If E is exponential and y is stable, then e raised to 1 by alpha y is metaglipher.
Wonderful, wonderful. Yes, yes, yes. I was just trying to that can be used for some estimation.
Estimation and generation also, random number generation. That is in fact the way that you have, sir has used for generating metaglipher.
I forgot it. That's right. Thank you. Thank you.
Thank you. Yeah, I think
Professor Tom.
Professor Kusu's,
Professor Tom.
yeah.
Hello, just a quick
Yeah,
comment.
Professor,
Thank you for the very nice presentation. You know, one property of the Mittag-Leffler distribution that I'm not sure if you mentioned in the presentation is the property of stability.
Stability.
So when you add Mittag-Leffler independent random variables and you have geometric number of those variables, then you have another Mittag-Leffler distribution, which is a generalization of exponential random variable, right, as well. So, and then let me just add, there's also like symmetric distributions, not on the positive half line, but symmetric distributions that also have this stability property with the geometric number of terms. And, you know, one of the reasons that it was useful for the modeling of exchange rates and financial type of data was precisely the stability property. I think some applications. So the stability is very crucial for some financial applications, which is why this Mittag-Leffler distribution was found useful in this arena. So it's just a comment about the distribution. It has very many fascinating properties, this Mittag-Leffler random variables. So I was very glad to see you talk about this topic. It's very interesting.
Thank you very much. Thank you.
Thank you, Professor.
Thank
you so much for your nice comment. Yeah. And in fact, we missed one of the presentation. Professor Kundu has not responded. Something serious, I think.
Right. So you couldn't get in touch with
some problems
him,
there.
right?
Yeah. I shall try to contact him in the evening, in the afternoon also.
Okay.
Now I think since he has not joined us till this time, we can conclude this session.
So
and
session,
join
right?
at they can join at 2 p.m. today. Next session. Since it is an online platform, there is scope for if he is ready, we can arrange his talk in the intimate you all the details. Otherwise, we can anyway. He will join with us tomorrow. We hope tomorrow the conference. Yeah. Before concluding the session, it is my for his nice presentation. Is an excellent way of approaches, and from starting from our professor, late Professor R.N. Pillai sir, we recollect him also during these deliberations, and our department in fact gets flourished through that that great professor, our R.N. Pillai, Professor Kusumu. Also, all of you know, I think so. I, on behalf of the Department of Statistics, University of Kerala, and all the meet, I extend our heartfelt gratitude to you, my beloved Professor Jayakumar. Thank you so much thank you for your nice talk and your support to our department and support to our activities. Thank you. Okay. Someone else is left and joining. So anyway, let us disjoin now. We can leave the meet for the time being and meet at 2 p.m. today.
Thank you so much.
After, I think, thank you, Professor. Thank you so much. Thank you all. Thank you for your patient listening and your support to our department, our activities. Thanks a lot.